Have you ever looked at an AI and thought, how can something so smart make such a simple, baffling mistake? It's a weird paradox, right? Well, today we're going to dive into that. We're going to uncover the art of teaching these models not just to memorize information, but to actually understand it.
So let's start with the big question. Why do these incredibly powerful models, which seem like geniuses during training, just completely faceplant out in the real world? The best way to think about it is like this. Imagine a student who crams for a test by memorizing the textbook, word for word. Ask them anything from the book and they'll nail it. But the second you give them a new problem, one that requires genuine understanding, they are totally lost. And that right there is exactly what's happening with our AI models.
The villain in this story actually has a name. It's called overfitting. This is what happens when a model doesn't just learn the important stuff from its training data, it memorizes everything. Every little detail, every quirk, and all the random useless noise. It learns too much. And this right here, this just lays it all out, doesn't it? When the model is working with the data it trained on, it's a superstar. It gets an A+, no problem. But the moment you show it something new, something it's never seen before, it completely bombs the test. It can't generalize what it's learned because, well, it never really learned it all. It just memorized the answers.
Okay, so to really get why this happens, we have to look at what drives the model. Its one and only goal is to minimize something called the loss function. Think of it like its report card or its score in a video game. The lower the loss, the happier the model is, because it means its predictions are getting closer and closer to the right answers in the training data.
And here's the kicker. The model becomes absolutely obsessed with this one single goal. Get that loss score as low as humanly or, I guess, artificially possible. But blindly chasing that perfect score on the training data is the very thing that leads it down this dangerous path of overfitting.
But hold on, it's not all doom and gloom. There is a hero in our story. It's a brilliant technique called regularization, and its whole job is to step in, pull the model back from the edge, and teach it how to actually generalize, how to understand the subject instead of just memorizing the test.
This is the big aha moment. Regularization comes in and completely flips the script by changing the model's goal. We're no longer just saying, hey, minimize your mistakes. We're adding a twist. We're saying, minimize your mistakes plus a new penalty for being too complicated. All of a sudden, being simple is part of the objective.
You know, there's a quote from our source material that it hits the nail on the head. By adding this penalty, we're basically putting a leash on the model. We're telling it, look, I don't want you getting obsessed with any single piece of information. Keep your internal logic, your weights, small and simple. We are actively punishing complexity.
Okay, so it's not like there's just one magic button for this, right? There are actually three main specialists we can call on to get the job done. We've got L2, L1, and elastic net regularization. Each one has its own unique way of encouraging simplicity. So let's meet the team.
First up, we've got L2, which also goes by the name Ridge. I like to think of L2 as the fair and balanced moderator at a debate. Its job is to make sure every feature gets a chance to speak, but no single feature gets to dominate the conversation.
So how does it do that? Well, L2 adds a penalty based on the square of a feature's importance. What that means is if a feature gets a little too loud, a little too important, its penalty gets huge, really fast. So L2 gently shrinks the influence of all the features, pushing them towards zero. It hardly ever eliminates them completely, which is why it's so good at creating stable models, especially when you have a bunch of features that are all kind of related.
All right, so if L2 is the friendly moderator, L1 is the ruthless editor. It's also known as Lasso. And it doesn't really care about making sure everyone gets a say. If a feature isn't adding serious value, L1 just cuts it. Gone.
And this brings us to the one word you absolutely have to remember for L1: sparsity. A sparse model is just a fancy way of saying a model with very few active parts. L1 automatically does our house cleaning for us.
It performs feature selection by tossing out all the noise and keeping only what's truly essential. L1's secret is that it penalizes the absolute value of the coefficients, not the square. And the geometry here is just fascinating. This penalty creates this sharp diamond-shaped boundary. And what happens is, the best solution often ends up right on one of the corners of the diamond, where a feature's importance is forced to become exactly 0. And that is L1's superpower, creating lean, simple, easy-to-understand models by making irrelevant features just disappear.
Okay, so L2 is great for stability, and L1 is amazing for cutting out the junk. But what if you kind of need both? Is there a way to get the best of both worlds here?
You bet there is, and its name is Elastic Net. Think of it as the hybrid coach. It's a really clever mix of both L1 and L2. It takes the ruthless editing from L1 to get rid of the useless features, but it also has that moderator quality from L2, where it can group together related features and make them work as a team. It really is all about finding that perfect balance.
All right, we've got our 3 specialists lined up, but the big question is, how do you know which tool to pull out of the toolbox for any given job? Let's make this super practical. This little table is your cheat sheet. If your number 1 priority is a simple, interpretable model, and you suspect you have a ton of useless features, you're going to reach for L1 Lasso. Now, if you think most of your features are actually important and you're more concerned about stability, L2 Ridge is your best friend. And if you're in a tricky situation with lots of correlated features, but you still want to clean house a bit, Elastic Net gives you that beautiful, balanced approach.
Let's just paint a quick picture here to make this super clear. Imagine you're predicting house prices, and you have 200 different features. L1, our editor, would look at 3 different ratings for the local high school and say, nope, this is redundant, I'm keeping 1, the other 2 are gone. L2, the moderator, would keep all 3 school ratings, but just dial down their individual influence so they work together. And Elastic Net, the coach, might get rid of a totally useless feature while also grouping those school ratings together to make them more stable. See the difference?
When you step back, you realize this isn't just some clever mathematical trick we're playing on the model. Regularization actually points to a much deeper philosophy about how to build good, intelligent systems.
It connects directly to this really old, really powerful idea, Occam's razor. The basic principle is that if you have 2 competing explanations for something, the simpler one is usually the better one. Regularization is basically Occam's razor for AI. It forces our models to find the simplest, and because of that, the most powerful and general solution. So, if you remember just one thing from all this, let it be this. Regularization is what transforms a model from that student who just crams for the test into one who actually understands the subject. It is the crucial difference between fragile knowledge and real, robust wisdom. And that leaves us with one last thing to chew on. We've seen just how powerful simplicity can be. But is the simplest model always the best model? Where do we draw that line between simple and too simple? Well, that's the art and the science of this whole field.